All right, calculus, we are looking at sample test 1, FRQs numbers 1 through 3. These are the calculator versions. This is an older format because in previous years, numbers 1 through 3 were calculator and numbers 4 through 6 were non-calculator. However, nowadays, it's only 1 and 2 that are calculator and 3 through 6 are non-calculator. Slightly different balance in the questions. Not a big deal, but just a quick note. Even though there's 3 calculator questions here, there are only 2 on the current ones. All right, let's get started. Number 1. Blah, 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 blah. Okay, I kind of cheated because I actually threw the graph in here already. But, you know, that's what it's going to look like. Just for time's sake, you can always graph this on your graphing calculator. I just inputted it here, x squared minus 8 over, I actually put 3 plus the x back. But same thing, x plus 3. When in my window, here's my window, from negative 10 to 10 in the x direction and negative 20 to 10 in the y direction. Why did I choose those numbers? Well, those are the numbers that were chosen here. So I just tried to match them. So here's part A. Cool. There it is. There's the graph. So now we're just going to answer a few detailed questions about this graph. We're already on part B. Look how fast that was. Wow, it's like super fast. Find the range of f. Use f prime of x to justify your answer. Well, check this out. If I figure out when the top would equal 0, this is what I'm going to find out. If I look at the top and then I factor that, that would be x, what is this, x plus 2 and x plus 4, which means that I have critical points at like x equals negative 2 and x equals negative 4. So take a look at what's happening. Now that's very true. Right here I have a critical point, and right here I have a critical point. And things change. In fact, I have mins and maxes there. But here is the crazy part. If I were to do like a sign chart with x and f prime, and let's say I look at, how about this, negative 2, and then we get negative 3, and then we get negative 4, and we're to look at in between these values as well. There we go. Alright, so here it's 0, here it does not exist, and here it's also 0. But what happens in between? Well, just looking at the graph, you can kind of tell based on those things. Between negative 2 and 3, this is negative. Is it negative? Yeah, it is. No, wait, what is it? What is the slope there? It's negative. That's right. And before it, it's positive. And then here, it is, no, it's negative again. And then we're positive after. So this is the crazy part that's happening. You know, we're increasing before, then we're decreasing, then we're decreasing, then increasing. And these ends are the key points because there's no more critical points before negative 2 or after negative 4, which means these are the end behavior. So it goes down, 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 and up, 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 up. So what are we saying? Because f prime is less than 0 when x is, or not is less than 0, is greater than 0 when x is less than negative 2, negative 4, pardon me. Oh my goodness, I'm getting these numbers backwards. This was negative 4, negative 3, and then negative 2. You guys are so confused right now, I know. There we go. Alright, then that means that the as x approaches negative infinity, let's put it this way, as x approaches negative infinity, f, not f prime, but f approaches negative infinity as well. And then also similarly, because f prime is also greater than 0 when x is greater than negative 2, f goes to positive infinity as x goes to infinity. This means, what's the range? Therefore, The range is negative infinity to positive infinity. It goes all the way down and all the way up. So that's kind of a loose argument there in the sense that it's not like we're using a lot of technical language. It's more common sense, but it is still using the idea that we have this slope is always going down and this slope is always going up because there's no more changes in it based on the evidence in f prime. Okay, this says find the limit of f prime of x as x goes to positive or negative infinity. Okay, so let's do a couple things here. When I look at this, I would multiply this out and I'd have x squared plus 6x plus 8 on the top, and if I multiply the bottom, that gives me x squared plus 6x plus 9. That's interesting. On the bottom, then if I take the limit as x goes to positive or negative infinity, let's see what happens. As x goes to positive infinity. There we go. So I'm going to multiply top and bottom by 1 over x squared. No big deal. There we go. Alright, so as we're doing this, I see that this would become 1 plus 6 over x plus 8 over x squared. And then the bottom would become 1 plus 6 over x plus 9 over x squared. So what is this limit as x goes to infinity? Or negative infinity, for that matter, whether it goes to positive or negative, it's going to be the same thing. It's going to be 1. Which means the slope at plus or minus infinity is 1. Ooh, now this is kind of crazy. We haven't really talked about this a lot this year, but that actually, when you have a slope, it kind of evens out on a specific slope. That gives you a slant asymptote. That means that we have, therefore, we have something called a slant asymptote with slope 1. And I think that's kind of the answer to part D here. What does it tell you about the graph of f of x? That stuff that I just wrote. We got a slant asymptote. In other words, it looks like this on the ends. Super cool. Alright, let's look at number 2. This is a little more traditional type question. Actually very common. In fact, this is one that you would likely see on the current AP test. Alright, so here we start. It says let v of t be this. It's a particle moving along the x-axis, so we're going left and right, horizontal. When t equals 0, the particle is at x equals 6. In other words, x of 0 equals negative 6, or you could say s of 0 equals negative 6. We're going to determine the position. We're going to write an expression for the speed. We're going to say which direction does a particle begin moving, and when does it turn around. We got a lot going on here. When, if ever, is the particle at the origin? Remember, the origin is really that point 0, 0. Alright, let's start with A. Determine the position of the particle at t. To do this, I need to see what v of t is and the initial position. Okay, so v of t equals 3t squared minus 12t. 3t squared minus 12t is v of t. And s of t, our original function you could say, is going to be s of 0 plus the integral from 0 to x of v of t. That's one way you could do it. Or we could just integrate v of t indefinitely and then use that s of 0 equals negative 6 to solve for the constant. Let's do it that way. Let's do that. So we have 3t squared minus 12t dt, of course. And that's going to become, well, we do just power rule for the first one. That gives us t cubed, or 3t cubed over 3, but the 3's are going to simplify. minus 12t squared over 2, and the 12 and the 2 becomes minus 6t squared, and plus some constant. So that's our v of t. V of t, not v of t, s of t, our position function, equals t cubed minus 6t squared plus c. Well, we know that if we plug in 0, we get negative 6. So negative 6 equals 0 minus 0 plus c. So guess what? C equals negative 6. All right, so S of t equals t cubed minus 6t squared, and then plus a constant, which in this case is negative 6. Okay, so it's saying at t equals a, all that's really saying is plug in a. That's easier than you think. S of a equals a cubed minus 6a squared minus 6. Check, done. There is the answer. For part A, let's go to part B. For part B, write an expression for the speed of the particle at any time t. Well, that is a piece of cake, because speed equals absolute value of velocity. That was it. That's all we really had to do. I mean, there are more detailed ways you can do it. We could even do it as a piecewise function, but hey, that works. Done. In which direction does the particle begin moving, and when does it turn around? All right, so interesting note here. We have a calculator, so let's use it. So I'm going to go ahead and draw v of t, which would be 3t squared minus 12t, or in this case x. So let's graph it. And here's the crazy thing. If you look at this, at t equals 0, it is automatically negative. We have a negative velocity. So negative. It is negative velocity. The initial velocity, our v of o, is going to be less than 0. Actually, it's 0 right at the beginning. But when does it begin moving? Let's put it this way. It begins moving in the negative direction. Well, what does that mean? In our context, we have, well, if we're moving horizontally, it's going to move left. First, the particle moves left first. All right. Now the second part of this question, when does it turn around? Okay, when does it turn around? That means change velocity. In other words, either plus to minus or minus to plus. Well, we start out negative, so when do we become positive? Let's take a look at this. It looks like we become positive right here. Now I would bet that that's at 1, 2, 3, 4. But if I really wanted to calculate it, just to be precise, I could calculate the 0 there. So that's what I'm going to do. Second, calculate 0. Number 2. Left bound, let's say it's between negative 3 and negative, or not negative 3, pardon me. Clear that. Clear. We got to do second, calculate, not between negative 3. I was looking for between 3 and 5. So in there, guess, I'm going to guess it's at 4. Hey, what do you know? It is right at 4. So the particle changes direction at t equals 4. And I'm going to do this just to show them, because if v of t equals 0, that means that 3t squared minus 12t equals 0. Factor out a t and a 3, then we got t minus 4. And guess what? T equals 4 is one of the times when velocity equals 0, because that's what's happening. We're stopping just as we're changing direction. Boom, yeah. Okay, part D. These questions are pretty fast. When, if ever, is the particle at the origin? Okay, for the particle to be at the origin, that means that our position equals 0. That we are at location 0. Well, we have a function s of t now. I believe it was t cubed minus 6t squared minus 6. And what we're looking for is, does this equal 0? Okay, well, graphing calculators, get them out, get them ready, plug them in. So this is going to be, what's this one here? It is t cubed, so x to the third power, minus 6x squared minus 6. I'm going to turn off the first function because I don't need it. Really don't need it. Okay, and let's see if we would be at the origin. Okay, so graph. And boom. Yes, we are right there. When is that 0? That looks like it's at 1, 2, 3, 4, 5, 6. But just to check, we do second, calculate 0, and I think it's at 6. So I'm going to guess it's between 5 and 7. 5 is the left bound, 7 is the right bound, 6 is my guess. And, ooh, I'm a little bit off. It's actually at 6.158. So, yes, it is at the origin when t is approximately 6.158. Check. Done. That's it. Okay, moving on. We're on number 3. We're almost done with this video. So here's our question. The number of minutes of daylight per day at 40 degrees north latitude is modeled by the function blah. Here's our function. Whoa, that's a messy function. D is the number of days beginning after 1996. January 1st, 1996, D equals 1. And for December 31st, 1996, D equals 366. Ooh, because 1996 was a leap year. That's interesting. Okay, what day D has the most minutes of daylight? Okay, the number of minutes of daylight is this. So this equals number of minutes of daylight. Okay, so what has the most? That's like the max of L of D. So that's what we're going to do for that one. What is the average number of minutes of daylight? Okay, average, that's the average value. We're going to calculate that in there as well. What is the total number of minutes of daylight in 1996? That's the accumulated value. Okay, so let's see what we would get. First, what's the most minutes of daylight? Oh my goodness. Well, it looks like we're going to have to put this in our graphing calculator. Let's go back and look at the function. There we go. Calculator. It looks like it's going to be, we can clear both of these. One six seven, pardon me, 0.5 times sine of, ooh, here we got a messy thing. This is going to be 2 times pi divided by 366 times, now we got something in parentheses here, the variable minus 80, close that off, close the sign off, plus 731. Now think about your x range here just for a second. We are going to be having this from 0 to 366 because that's how many days are in a year. Let's count by, I don't know, tens, just to make it a little cleaner. Now we wouldn't have 0 number of days, or 0 number of minutes in the day. We'd have, or negative I should say. So we have at least 0. We probably definitely have more than 10 minutes a day if you think like 60 minutes in an hour and half the day, 12 hours, 16, 12, 7. So we're looking at like 800 minutes maximum maybe. But let's go for 1,000. So 1,000, we're going to count by 100s. Alright, so let's graph this. There we go. So this is saying that right about here is the maximum number of days. or maximum number of minutes of sunlight in a day. Okay, so how can we calculate that maximum? Perfectly with our calculator. Second, calculate maximum for, and it looks like it's going to be between this value and this value. We're going to guess that it's about here. And it occurs at day 171 and a half. That's about 898 minutes and a half minutes. Okay. So, first question. What day has the most minutes daylight? Well, and this is justify your answer. The max of L of D occurs at, day 171, right in the middle of the day, of course. And what else can we say about that? It says justify your answer. So we're going to say because L prime of D, we could say L prime of D equals 0 at that point, and L prime of D changes, the slope changes from positive to negative. There you go. That should be enough, because just by looking at the graph we could say those things. All right, let's look at number B, or part B here. What is the average mean value of the number of minutes of daylight in 1996? Okay, the average value, average number of minutes, is an average value calculation. So the average value equals the accumulated amount over the total interval, pretty much. The average value equals the accumulated amount, which is going to be the integral from a to b of whatever function we're doing. In this case, it's L of d, dd. That's funny, lots of d's in there. dd, and then over b minus a. So what are these limits? Well, the lower interval, we're starting from 0. We're going to day number 366, and we're going to put in our function L of d, and then we're going to divide by 366. So let's see what we would get then. I just got to integrate this. So second, calculate the integral, which is number 7. We're going to start from 0 and go all the way up to 366. Boom! So that's going to be 267,546. That equals 267,4. What was next? Oh, I forgot that. 546 divided by 366 minutes. And guess what? We don't have to simplify that. Why? Because it's an FRQ. So we're done with B. Let's move on to C. And that was enough justification of our answer, showing just the process that we set up to get that. We don't have to use verbiage necessary to justify it. What is the total number of minutes in daylight in 1996? That is just the accumulated total. Is going to be the integral from 0 to 366 of L of D. And guess what? We already figured that out in part B. That was 267,546. 267,546. Check. Done. Stick out your tongue. Alright, next coming is the non-calculator. Ooh, the scary stuff. Numbers 4 through 6. Okay, stopping the video here. Going to convert it, upload it, and have it ready for you guys in just a few minutes.